Sergio, you are the responsible for the second paper, is it?
Yes, yes. Can you hear me well?
Yes, yes. Thank you, Sergio. Alexandre, are you planning to play the video for the presentation?
If it is better, can be.
Okay. Sergio, the same? You are planning to play the video?
Yes, yes.
Okay. Deborah, the same?
Yeah, me too. I have a question. I shall share my screen or you uploading it?
What? The video?
Yeah, I shall share my screen or you share
No,
the video?
no. Usually the organization here play the video. Is it,
Okay.
Bruno? Can you confirm for us? Julio? No, Bruno is not here. Julio?
Yeah. We will play the video for the participants if they want. You can also
Okay.
play the video yourself if you want.
Oh, I prefer you share for me. Thanks.
Okay, no problem.
Perfect, Julio.
So I'm just waiting for you, Professor Drews. You can start when you want. We are already broadcasting to YouTube. So I think we still are 5 minutes early. So I think we can wait a bit more so more people can join.
Yes. I think you can wait. And our session is a little bit smaller than usual, so it's not an issue to wait a little bit. Let's start our session. We can start, Julio. Is everything okay to start?
Yeah, for me it's okay. When
Okay.
we can start when you want.
Perfect. So, good afternoon, everybody. My name is Paulo Drills. I'm professor in the University Federal of Rio Grande. And I'd like to say hello to everybody, and I'd like to thank you, the organization of the LARS, by the invitation to be chair of this session today. The session VSM3, Vision, Sensing, and Mapping number 3. In this session, we will have 3 papers. The first paper is Improving the Mobile Robots Indoor Localization System by Combining SLAM with Fiducial Markers, authored by Alexandre Júnior, Luiz Piardi, Paulo Leitão, and Eduardo Bertonha. So, we can start, Alexandre?
Yes.
Julio? No sound?
Hi, my name is Alexandre Júnior, and I will present about the paper Improving the Mobile Robots Indoor Localization System by Combining SLAM with Fiducial Markers. This work was developed.
Yes, now just sound, no images.
Hi, my name is Alexandre Júnior, and I will present about the paper Improving the Mobile Robots Indoor Localization System by Combining SLAM with Fiducial Markers. This work was developed by me in partnership with the researchers and professors Luiz Piardi, Eduardo Bertonha, and Paulo Leitão. This presentation will be divided in the following topics: the introduction of the subject, a brief review of the architecture of the indoor localization system, the implementation of the localization system, the results, conclusions, and future workers. It's commonly known that mobile robotics have a high demand for indoor applications. But for a robot to be able to perform tasks, is required to have a robust localization system to determine the position and the orientation of the robot relative to the environment. But that is not a simple task that, given the complexity and dynamics of indoor environments. I ideally use strategy to the localization in indoor environments is simultaneous and localization and mapping. This method allows a robot to generate a map of its surroundings based on the information collected from a sensor, such as a LiDAR, and based on this information, doing the localization of the robot simultaneously with the generation of a map of the environment. But this localization is still subject to some errors due to the lack of precision of LiDARs or even from the odometry of the robot. This can be minimized by using some algorithms like the Adaptive Monte-Carlo Localization, AMCL, which make use of a particle filter to estimate the robot's position, having some, in this way, a better localization of the robot. But even in this way, using SLAM and MCL, the position estimation of the robot can still be subject to some errors, especially in environments with dynamic obstacles or with lack precisions, which, for example, in long hallways, which make it difficult to determine the position of the robot. especially when the robots don't know his initial position, the L-no kidnap robot problem. With this in mind, the localization system proposed in our paper seeks to integrate SLAM and AMCL with the detection of fiducial markers stored through indoor environments. Fiducial markers are elements commonly used as visual reference points that have a well-known shape and size. In this way, when are they detected by a camera and use some artificial visual strategy, it's possible to determine the distance between the camera and the markers. So if we have a camera on the top of a mobile robot and we know the position of the marks is spelled from in the environment, we can determine the real position of the robot based on the markers and update this information to the AMCL algorithm. In this way, reduce the errors. Here we have a simplification of the architecture of the system. So basically, in the environment, the robot will be collecting some informations. We have the odometry of the robot and the LiDAR sensor. This information is used by SLAM and AMCL to localization the robot and estimate the position of the robot. In the same time, a camera on the top of the robot is looking for fiducial markers in the roof of the environment. So when a mark is detected, algorithms that use the visual artificial vision strategy, you determine the distance between the camera and the robot from the marker, and this information will be used to see in a database where exactly this marker is positioned in the environment and determine the real position of the robot. This information is updated to the AMCL algorithm, in this way reducing the errors existent in the estimation of the robot. The implementation of the localization system was made using ROS, the framework, because we have a lot of already implemented packages that can be used to localization a robot, like the SLAM and the AMCL. And we have also some packages that help us to determine, localize, and determine the position of markers. We create a simulation environment based on the hallways of our university. In the VRAP simulator that have connection with ROS, we create a representation of this environment, the hallways of the university, just like we can see here. And we create, we have mobile robots with a LiDAR sensor and a camera on the top of the robot that is used to detect some fiducial markers. These markers are that we use are native from the package RTrack Alvar that can be used in the ROS to detect the markers and determine the distance existent between the marker and the camera. So use our algorithm, we can make the calculations necessary to get the distance of the markers from the robot, seeing the database where those markers is, and update this information to the AMCL algorithm. Here we can see a representation of one of the simulations. Here we have the robots navigate in the environment. Always that marker is detected, the position of the robot is updated to the AMCL to reset all the intrinsic error accumulated from the estimation of the robot. We made a lot of tests here we will present some of the results. We have here the generation map generated by Slan and the routes that we use to do some tests. We do a lot of tests, but we will present just a few of the results. Here we focus in the kidnap robot scenarios. That means that the robot did not know his initial position, so the text, the fiducial markers are important to help the robots to determine his initial position in the environment. In the same time that always that a marker was detected, the estimation of the position of the robot was more accurately than when was just used SLAM and MCL. We can see that the robot was lost. Né? The real position of the robot don't coincide with the estimated position, so the algorithm think that the robot is in the route correctly, but he is not. In the strategy used the fiducial markers, this problem does not occur. Here we have the same case with the kidnapped robot scenario, but in the second trajectory, here we see that with the first strategy, just use SLAM and MCL, we have a little bit better estimation of the position in each route, but it still has a lot of discrepancy between the real robot position and the position estimated by the algorithm. When use the fiducial markers detection, the real position of the robot and the estimation position has more accurate results. So the combination of the SLAM and AMCL with the fiduciary markers position track has been shown to be an effective indoor localization system method. We want to test, do more tests involve dynamic obstacles in the environment and more complex routes. And we also implement the system to a real robot, so to be tested in a real environment with people and obstacles moving in this environment to see if the strategy is really effective. Thank you everyone for your attention.
Thank you. I don't know if anyone have a question.
I believe Professor Drew's having a connection problem. But if is there any questions from YouTube? So okay, I will just carry on with the questions. It seems that you have placed the markers on the ceiling. It's a very nice idea. Won't they have any illumination problems because they don't get a direct light? So it might be a bit harder to detect them. And also, I believe you don't have the problem to detect the whole ceiling. So you are usually getting a very big picture. So you just know exactly where the marker is. But did you have any problems with detecting the markers because of illumination?
We position the markers in the ceiling just already speaking, because like is always have people walking through the hallways. So the idea of position them in the ceiling was just think on that to not broke the vision, but is some problems with illumination. We try to pick places that the lights on the ceiling will not interfere in their localization, because all the distribution was already think on the lights. But sure, we have some problems with lights. We made the test within simulation, but now we are testing in the real environment, and some tags will be necessary to be replaced in some positions of the environment. And also we have some problems that make sure that the tag is positioned in exactly the place that is in that we put in the database, to not put some errors in the algorithms. So some are many problems that we are looking for to try to solve and make sure that the results will be satisfactory.
Thank you, Alexandre. I had some issues with my internet, but now I'm able. I have just a last question, since you have a little bit time. My question is related about your indoor localization. I know that's the problem. You don't have like GPS or other sensors. Do you think, at least for your next step, the practical, to use, for example, this network or some other source of location, for example, Wi-Fi? Usually the guys are using Wi-Fi for improve indoor localization. That's your problem, to fuse together everything together, right?
Yes, we thinking better the algorithm. Wi-Fi is a thing that we already think about, but we have a lot of problem of connection with Wi-Fi in the hallways. So, for example, when I was constructing the map of the environment, I was using Wi-Fi to communicate with Ross to send the teleop signals to the robots, and move the robots for the environment to creation of the maps. And just doing that, I already have some problems with connection. So maybe our environment is not ready to use some strategy using Wi-Fi. Maybe Bluetooth is not already so good. So we're gonna have to think about how can we improve the localization using another strategies, outro with LAN and the markers.
So thank you, Alexandre.
Thank you.
More question. Our time was finished. Thank you. Now I invite the next author for this session. I'd like to invite the authors of the paper, A Framework to Improve SLAM Algorithm for Crowded Human Environment. The authors are Kevin Unofuentes, Sergio Jr., Denis Aranibal, Judith Cardinali, and José Diaz Amado. So I'd like to invite Sergio to present for us. We will start with the video of the presentation.
Good afternoon, everyone. Am I supposed to share my screen, or will show our video?
I think Julio will play for us.
Okay, thank you. Hi, my name is Sérgio Ferreira Andrade, and I am here to present the paper, An Approach to Improve Simultaneous Localization and Mapping in Human-Populated Environments. The work was developed by Kevin Ofuente Couque, me, Sérgio Ferreira Andrade, Denis Barrios Aranibal, Judith Cardinali, and José Dias Amado. This work was supported by Fundo Nacional de Desarrollo Científico, Tecnológico y de Innovación Tecnológica, Fundecit, as executive entity of CONCITEC in the project RUTAS, Robots for Urban Tourist Center Autonomous and Semantic-Based. Now, I am going to do a brief contextualization of our work. One task that autonomous mobile robots have to perform in indoor spaces is to construct the map of their environment and report their location and orientation. This process is called simultaneous localization and mapping, SLAM. To do so, robots extract data through their sensors. To solve the SLAM problem, algorithms based on probabilistic filters have been proposed, such as the Kalman filter and the particle filter. These are base methods for the implementation of various classic SLAM algorithms, such as G-mapping, TinySLAM, and IEKF-SLAM. However, in dynamic indoor environments, moving objects induce the SLAM process to collapse or diverge. Moving objects should not be taken into account to generate the map, and the occlusions that they generate should be solved. A few examples of dynamic environments are hospitals, schools, and museums. In this work, we propose a robust and flexible approach for SLAM algorithms to perform better in human-populated environments by integrating a filtering scheme that manages moving and static objects. A classic SLAM algorithm follows the process marked with the green blocks. We extended it with the modules between the perception of scenes and the application for SLAM algorithm, as shown with blue, dark green, and red blocks. The added modules solve the management of the input data and the occlusions generated by dynamic objects. Basically, the schematic of the proposed solution consists in three phases: an initial phase that consists of the scene perception, a filtering phase, and the SLAM phase. The scene perception module allows gathering data from the robot sensor. A diagram of an example of this process is shown in this figure. In the diagram, right, left, and front topics are mentioned, since the proposal follows the Robot Operating System (ROS) communications protocol, so each topic contains the data of each sensor of the robot. Callback functions are used for the nodes of ROS to obtain the laser data. The adaptation of laser data as input to the filter module comprises the management of the type of messages provided through the sensors to be manipulated. This module translates those messages representing the characteristic of a type of sensor data, such as coordinates, distance, and orientation, so they can be understood and processed later by the filter as appropriate. The segment objects module includes the capacity of discerning and separating static objects and mobile objects. To perform this role, the proposed algorithm uses the run-seq method. Nevertheless, it can be substituted by any other filter that performs similar. This figure shows the detailed process of this module, but we are going to explain it later. The scene module with only static objects receives the run-seq filter output data vector, which is basically the filtered data, while the scene module with moving objects only receives the data that will be discarded, since it is not necessary to be included in the environment mapping. Therefore, only the filtered data contained in the scene only with static objects module are published as data to be used later. Since the structure of a robot can contain multiple built-in sensors, we propose a run-seq method for each sensor. Thus, its performance is improved. This data published through each sensor of a robot have to be joined and its results are sent to SLAM as shown in this figure. In our approach, any classic SLAM algorithm can be integrated. As an example, we take G-mapping, which uses a particle filter. Therefore, each sample estimates both the pose of the robot and the map of the environment. and the resampling stage allows the algorithm to reach the most probable estimate. The application of the mapping algorithm can usually be outlined as shown in this figure. To validate our approach, we performed a battery of tests in a simulated environment consisting of ROS Melodic, Gazebo 9 Simulator, and RVs, which work by default on Ubuntu operating system. We simulated 3 words which represent different cases that the robot can face in a museum. The first word represents an empty museum where there are no people moving, so the robot only notices pure static objects. The second word represents a museum with people still in the same place and static objects. Static people in the environment are simulated with models of human beings. The third word is a museum with people in motion using objects called agents, which physically take on the appearance of rectangular boxes in motion. This word is crucial as it allows testing GMAP divergence in dynamic environments. We simulate the Pepper robot since it's a robot that can be used in social environments due to its architecture, which is perfectly suited to analyze land behavior in crowded environments. This is how the Pepper robot looks in the simulated environment. This robot contains 3 laser sensors in parallel at the base of its lower body, which provides the necessary data from the environment. After configuring the parameters of gmapping, the generation of the first word map can be visualized in this figure. The generation of the second word map is shown in the left. The difference between this figure and the previous one is that the second shows static people who were recognized by the laser sensor, and they can be clearly appreciated in the construction of the map like black dots. The generation of a third word map applying the GMAP algorithm with the configured parameters is shown in the right. This map of the third word shows how the GMapping algorithm diverges when building a crowded and dynamic environment map. In this image, we can see black dots reflected in the white spaces between the walls. There are people who circulate in the environment. Gmapping uses a scan matching algorithm called ICP that does not fail when receiving only inliners. However, when it receives mixed data, inliners and outliers, the ICP method performance degrades and generates disturbances on the Gmapping algorithm. For this reason, we consider to include a filtering step before entering the slim process. For these experiments, we implement the runsec algorithm as the filter executed before performing Gmap. The runsec algorithm is implemented to return a mathematical model that it considers sufficient to discern the inliners and the outliers points. Points considered inliners are static objects, and outliers are dynamic objects, or people moving the environment. To illustrate the example of how the runsec algorithm works, we have here a set of dots from the laser point cloud data. In order to find the best model, at first the runsec algorithm generates several curves. The curve with the best score is the chosen one. This score is calculated using a threshold and using it to count the number of the closest points that the model has. Finally, runsec finds the model with the highest score or the closest objects. For the specific case shown in this figure, the algorithm chooses the model that best fits and distinguishes between static and dynamic objects. At the end of this process, we have the filtered data from the frontal laser point cloud that runsec model has declared as inliners. Now we can see the result obtained with our approach for the third world map. Compared with the map generated with gmapping without filtering, the improvements are visually obvious. The dynamic objects plotted with our approach are around 20% less than the ones generated with gmap without filtering. Nevertheless, the static parts of the environment are much better appreciated with our approach, reaching an improvement up to 80% compared with the classical gmapping. So, we proposed an approach to improve SLAM solutions for dynamic environments with three phases: initial, filtering, and classic SLAM phase. Through this approach, with this configuration, an improvement was obtained in the construction of the dynamic environment map. Another important contribution of the present work is that the second and the third phases are interchangeable. To illustrate our approach, in the second phase we use run-seq algorithm, and the third phase we use gmapping algorithm. The filtering technique can be replaced by another, such as convolution, and the classic SLAM can also be replaced by another, such as Hector SLAM or Time SLAM. As future work, quantitative results of the error of different approaches will be obtained. Thank you very much for your attention. If you have any questions, you can do it now or contact us via email.
Thank you, Sergio. So, any question? Let's see, any question? I will start with a question. I'm not sure if I understood exactly the things, but your idea is to do a kind of classification in the point cloud in order to avoid to use mobile points or points that can move. Is it, Sergio?
Yeah, it's kind of it. We try to discard the data that are not useful. The data that do not represent static objects.
I also understood that you did it using simulation, is it?
Yes.
Okay. My question is, do you evaluate the capability of the method to deal with different level of crowded environment with different numbers of people or something like that? Do you evaluate that?
Actually, we chose some a quantity of objects, of mobile objects that we by intuition we considered as a lot, but we didn't made a study for different numbers of people circulated in the environment. Is a work that we are going to do in the future to variate the number of people and the algorithms that we use to variate. For example, using another filter and using another algorithm, another SLAM algorithm.
Okay. I have another question, Sergio. So the main problem that you have here is to classify a point if it's static or dynamic, if it's smooth. So when I think in classification problem, I think in neural networks. Nowadays is the state of the art for most of this application. Do you think in try to use neural network to classify these static versus dynamic objects?
Yes. The filtering scheme was an option that we had an idea that felt suitable for what we planned to do. But of course, neural networks can be very useful and how can I say, very applicable for this problem.
Okay, thank you, Sergio. No more questions.
I have one question for Sergio.
Okay, Luis, go ahead.
First of all, congratulations for your work, Sergio. I was thinking in the next step, if we using this classification that you do with identify peoples and dynamic objects in the environment, it's possible to use this information to create uh, a path to the robot, avoiding obstacle. For example, if have people in the environment when the robot will navigate, using this information that you remove from the map is possible to use to avoid obstacle.
Actually, the path planning is not our goal in this project.
Yes, I understand.
But there are some colleagues of us that work with social restrictions to build the path planning, and actually this work is part of a bigger work where some groups where each group has the responsibility of executing one task. Ours was this land part. But I believe that maybe, because I don't know, because I never tried to do planning. So now I can't actually give you a answer.
Yes, because in your work that I understand, you do something difficult that is identify dynamic objects in the environment. So this information can be useful to realize, to execute a path with free obstacle. It's very interesting.
Thank you.
So thank you, Sergio, for your work and your presentation. Let's go to the next and last paper of this section, VSM3. I'd like to invite the authors of the work, Performance Comparison of Convolutional Neural Network for Object Detection in Free-Red Balloon Imagery. The authors are Débora dos Santos, André Fransani, Marcos Máximo, and Arthur Ferreira.
Hello, I'm Débora dos Santos. I'm going to present you performance comparison of convolutional neural network models for object detection in tethered balloon imagery. A work done together with André Fransani, Marcos Máximo, and Arthur Ferreira. And first, to contextualize this work, we can think of various situations that require the coverage of large areas, such as forest fire detection, border defense, security of urban events, and so on. And the solutions in this kind of situation have converged to the use of unmanned aerial vehicles to acquire data. And once this data is acquired, which means mostly images in this case, we want to detect objects of interest on it. So we can use neural networks for this purpose, as it is already a well-consolidated technique. So for this work, our main goal is comparing state-of-the-art architectures using Altavis tethered balloon imagery. Altavis is a company that provides intelligent monitor systems based on aerial vehicles and provided us the data set. And also, we have this contribution of providing an extensive comparison of networks and training techniques, specifically on UAV imagery. So now we can move for some theoretical background. And starting with deep convolutional neural networks, they work by being fed images and outputting a class and a bounding box. The class is the label of this image to what category it belongs, and also the bounding box will give us the location of this object in the image. And here in the middle box, we have our convolutional neural networks, what of course has some convolutional layers that are responsible for extracting the features of the image. And next, in the layer steps, there is some fully connected layers that perform the classification and regression tasks. And by using different CNN architectures, we can achieve different results. So this can be explored. And specifically, the feature extraction layers can also be explored. And another name they are known by is backbones. So next, I'll cover some state-of-the-art architectures of convolutional neural networks. The first one is faster RCNN, and this is a two-stage detector, which means it first proposes regions of interest and later classify the objects in them, and this leads to a higher accuracy. And for the specific case of faster RCNN, it achieves a higher speed in comparison to the models that came before it by using a specific set of size of anchors to look for those regions. And in contrast, SSD is a one-stage detector, which means it doesn't look for a region of interest, it just performs tasks in a single stage, and this leads to a faster computation. And SSD achieves a higher accuracy in comparison to the models that came before by scaling down the feature map. So it will look for bounding boxes in all the different sizes feature map, and then can detect the big objects as well as the small ones. Our third architecture here is RetinaNet, and it has a similar approach with the last one. It can retrieve differently sized objects, and it does it by using a feature pyramid network. And the final model is YOLO. It works by dividing the image in a grid. Then it will look for bounding boxes in each cell of this grid, and later it applies a no-max suppression technique to select the best fitting bounding boxes for each of those cells. So we can move now to the methodology of this work, starting with the dataset. It was acquired by Altavio during its commercial operations with Tether Balloon, and due to the privacy of clients, it's a private dataset, but it contains 2073 images that are hand annotated with three classes: person, vehicle, and boat. This dataset is highly imbalanced. We can see that we have much more objects of the vehicle class than we have of the boat class, and it's important to note it because this can lead to different techniques choice when we are training the network. However, when we split this dataset in the training, validation, and test sets, we keep this proportion. And for the chosen architectures, we use the form mentioned before, and we do apply the backbone variation for the two-stage faster RCNN. So which means that it leads to 7 main models that will be used for experiments, and I will refer to them by those capital letters just for the sake of simplicity. So for training setup, we have, besides the backbone variation, transfer learning, and we use it based on the COCO dataset. We also have varied learning rates, and we also apply the multi-step schedule, which means the learning rate decays as the network converts, and we also applied an optimizer on the loss function. So we have varied hyperparameter combination that are tried on those 7 main models that were defined before. And to evaluate those models, we use 2 main metrics. First is the mean average precision, that is a widely used metric in the detection task, and it works by setting a confidence threshold of the intersection of overunion. So we can be more strict about the location of the detected bounding box. It has to fit more the ground truth, so we can set it to 75%. We can be less restrictive by setting to 50%, and we can have an idea of how it works in different thresholds by using the COCO map that I will refer as map all later on. And also there's another metric that is important when dealing with real-time applications, that is inference time. This is the time that the network takes to detect objects in an image. So let's see the results. Here is a summary, It only shows the best training case of each model. Also, I just showed the models that are the best ones in each of those metrics. So starting with the map 75% and map all, we can see that model E achieves the best result, and this is RetinaNet, and this is architecture that can deal with multi-scale objects as well. It balance hard to detect examples. But if we look to map 50, we can see that model F has the best performance. In this application, we don't need to be strict about the location of the bounding box. As long as we do detect this object and we have a rough location of it on the image, it suffices the monitoring task. And the final metric we can observe is the time. For model D, it achieves the best inference time, that is 70.9 milliseconds in the setup we used. This is the best time achieved between all the models, but if you look to model F, it just roughly is lower than model D. And this is a difference that don't matter this much. So you can conclude that model F, YOLO, is the best option for this application as it balances the accuracy and inference time. And next, just to illustrate some detections of YOLO, in the first row we have the ground truth, and the second row we have the detections. And we can see that this model is very accurate, and even detects here in the park image car in the corner that was not annotated in the ground truth. So we can better evaluate the YOLO model by looking for each class metric independently, and we can foresee that the vehicle class has the best average precision, but still it has a high number of false positives. But by looking the image, we can see that it's actually correctly predicted cars, just as in this image, that are not annotated originally because of the guidelines of the annotation. So we can see that this network has achieved a good generalization for this class. Next, we have the lowest average precision for the person class, and you can see that it has a high number of false negatives, and this happens because we have many images that contain person that are not contrasting against the background, so they are difficult to detect. And also the bot class had a high number of false negatives that correspond to the larger bots, so it was not able to generalize for those two classes, and means we need more objects, more examples for further training. So summing up all the work we've done, we used 4 main architectures. They are training for the tethered balloon imagery that was labeled with person, vehicle, and bot class. And we saw that inference time suffices the real-time monitoring requirements, and YOLO model has presented the best trade-off between accuracy and speed, so it was chosen as the best model for this application. So for future work, we propose that the dataset must be increased and balanced, providing more examples of the hard-to-detect objects, so the network can generalize better. And we can also explore more data augmentation. And for those architectures that are based on a set of anchor boxes, we can explore clustering techniques for defining their size. And finally, we can evaluate new state-of-the-art architectures. We can explore the most recent ones and see how they perform in this task. So finally, I just want to thank CNPq for the financial support and Otávio for helping throughout the execution of this project, and thank you all for the attention.
So thank you, Deborah, by your presentation, your interesting work. We did a very nice evaluation of the state-of-the-art network for this detection problem. It's very interesting. I think your work was developed last year, so this year we have the YOLO V5 that can try to help you. I'm not sure if to help you a lot, but I have one question. Since your problem is classification of outdoor objects, for example, a car that you are looking from a balloon. Do you evaluate the effect of the environment changes? For example, if you have hazy, foggy, or a sunny day with a lot of light, how YOLO deal with variation in terms of illumination and condition for the classification? Your data set is like variate enough. They have these different conditions, or these conditions are not interesting. I don't know. I'd like to know more about these situations.
The data set is quite small, actually, because it just contains some specific situations and context scenarios. So we don't have much background and context variation, actually. We mainly focus on the object classes detection evaluation to see how each object is being detected and how the network is performing on each of them, but didn't really evaluate the context because we don't have this much variation.
No, yes, it's interesting. I was thinking about that. Usually when we try to classify outdoor objects, for example, usually this question appears. But in your case that you have a balloon, for example, I don't believe that you fly with a balloon in a rainy day with or with
exactly.
windy, strong windy day or a foggy day or something like that. You can try to justify this focus on like flyable situation or situation that the balloon can fly. Are the data that you have that can be one interesting justification for your, because outdoor environment, usually this question or this evaluation are required to be done. So we have more questions. Let's see, no YouTube question. I'd like to thank you, Deborah, for your presentation, for your work. So I'd like to thank you, our authors, and I will close our section VSM3, Vision, Sensing, and Mapping number 3. Thank you a lot. And now at 3 p.m. in Brazilian time, we have the section AAV, Aerial and Aquatic Vehicle number 3. In few minutes, in 7 minutes, the next section will start. So thank you, everybody.
Thank you.
Thank you, bye.
Thanks.
The word is yours, Marcelo.
Hey, Paulo. Como é que tá? Tudo bem?
Tudo bem. So, I think you have some minutes to start.
Professor Becker, I will take care of the video playback if the authors want.
Okay.
And we can start when you are ready. We still have some 6 minutes.
Yeah.
Yeah.
That's okay. Are all the authors here?
I believe it's better to have a ready check. I don't know if they are there.
Okay. So as far as understood, they have 10 minutes and 5 minutes for questions. 10 minutes, the presentation is recorded, so you play the presentation.
Yeah,
Right?
if they want to, yes.
Mm-hmm. So I see that Luis is here. It's the first paper that's going to be present. Pedro is the third one, is here too. Oh, is there someone from Federal University of São Carlos? Lydia, Pedro, King, Isaac, or Eduardo? No answer. So they are the second paper. And the last one is from ITA. João Dantas, André Costa, Diego Geraldo, Marcos, and Takashi. So, hello everyone. I think we can start. 1 minute. Welcome everyone for the aerial and aquatic vehicles number 3 section. We are going to have 4 papers present this afternoon. And I would like to invite the first one, Cooperative and Decentralized Decision-Making for Loyal Wingman UAVs, from Luiz Giacomozzi Jr. from ITA, Instituto Tecnológico de Aeronáutica. Please.
Good afternoon, everybody. Good afternoon, Marcelo. And I would like to ask you if you can present my video, please. Thank you.
Hello, my name is Luiz Giacomozzi. I am a graduate student at the Instituto Tecnológico de Aeronáutica, and I'm going to present our paper entitled Cooperative and Decentralized Decision-Making for Low Wingman UAVs. The other authors of this paper are Professor Steven Schwantz from the Eindhoven University of Technology, José Fernando Brancalhão from Embraer, and Professor Marcos Massimo from ITA. The overview of this presentation is, I'm going to introduce the context, then I'm going to proceed to the main decision-making architectures found in literature, the scenario of interest where we apply the Loyola-Wingman concept, the simulator that we developed for this paper, the decision-making development for a kamikaze UAV and for the Loyola-Wingman UAV. Then I'm going to proceed to the experiments carried on and the results, and I'm going to conclude and show ideas for future work. The term decision-making is the cognitive process resulting in the selection of actions among several possible alternatives. Modern decision-making enabled the so-called cooperative engagement capability among multiple networked agents that work as a team in a network, make decisions in group to engage and disable aerial threats. Those agents can be manned or unmanned aircraft systems, also known as manned-unmanned teaming. This idea includes the concept of a loyal wingman aircraft that works under the tactical command of a manned leader. This aircraft can be replaced by UAVs. With the combination of these UAVs with artificial intelligence, we can automate most of the decisions done by combat UAVs, achieving an autonomous UAV that can be used to allow the human pilots to focus on the big tactical picture in modern warfare scenarios. Decision-making architectures. The most popular methods found in literature are the finite state machines and the behavior trees. Both methods are often designed by humans. This design is empirical and based on good practice. This process is iterative, with the agent performance being evaluated by experts in the area or through statistics. Optimization methods and machine learning techniques can be employed to optimize parameters or to learn new behaviors for these agents. The decision-making can be broken down into so-called behaviors, which are models tailored to solve subtasks in the context. State machine is the simplest and the most common technique found in decision-making. The agents only have a finite number of states. The states represent the behaviors for the agent. The machine guarantees the permanence in a certain state, unless there is a transition. The developer is responsible for defining the behaviors, or encoding the behaviors, and in the conditions that are triggered. These conditions can often be represented as parameters in the system. Behavior tree. The behavior tree has become the standard decision-making method in the AI games industry, as it solves many problems encountered with the FSMs. It changes the decision-making paradigm to a tree, where the behaviors are coded as nodes. There are two types of nodes, compose node and leaf node. The compose node controls the behavior tree logic, and the leaf node executes the behaviors or check conditions. Here you can see a condition and a behavior. The node returns a status, success, failure, or running. For example, the sequence node will execute all the nodes on the left branch and then proceed to the right branch. If one child fails, he will return failure. In this table, you can see all the logic present in all the nodes. Scenario of interest. In our paper, we introduce a novel scenario based on the Loyola-Wingman application. This scenario has two teams, a mom team and a kamikaze swarm. The mom team is composed by Loyola-Wingman agents and a leading drone. This team must engage and disable these kamikaze drones that are trying to attack both the protected area and the leading drone. The simulation is considered over when the leading drone is destroyed, when the protected area is hit by 5 drones, or when all Loyola-Wingmen were destroyed. The leading drone is controlled by a human. All Loyola-Wingman's agents are autonomous. The Loyola-Wingmans have two kinds of guns, a freezing gun and a vaporizer gun. The freezing gun is a mid-range gun, and it slows down the threat. The short-range gun is the vaporizer gun that destroys the threats with a single hit. A simulator was developed for this study. It was developed using Python and the Pygame library. The UAV model is composed of a position controller, which controls the pose of the drones, and a collision avoidance model using the potential foods technique. The simulator is intended to evaluate the application of the Loyola-Wingmans in the scenario proposed, where we focus on the evaluation of the decision-making techniques, abstracting realistic physics models. The simulator can be seen in figure 5. Here we can see a kamikaze swarm attacking both the protected area and a mom team. In figure 4, we can see the leading drone at the center and 10 Loyola-Wingmen surrounding him in a protective formation. The decision-making for a kamikaze is pretty simple, and it was developed using a state machine with each kamikaze having an identical copy of this machine. There are 4 behaviors. The default is the wait state. In this state, the agent will wait for the definition of a target to attack. Once the kamikaze chooses a target, he will seek this target and remaining in this behavior until it is destroyed. The targets are chosen with equal probability, and they are the leader, or the protected area, or the loyal wingman, a specific one. In this state, the kamikaze will choose the closest loyal wingman to attack at every 1 second. In this figure, we have the behavior tree for a loyal wingman agent. The behaviors are 5. Chase threat, go to formation, attack using vaporizer, freeze threat, or sacrifice. The default behavior is go to formation, where the loyal wingman will remain in the formation to protect the leader. Once a threat is in the engagement range, the behavior tree will execute the chase threat behavior. Here, the loyal wingman will leave the formation in order to pursue the threat. When the loyal wingman is in weapons range, the behavior tree will select one of the possible alternatives to attack the threat. It can be by using the vaporizer gun, the freezing gun, or by sacrifice. Usually, the loyal wingman will first slow down the threat by using the freezing gun, then he will get closer to the threat and use the vaporizer gun to neutralize it. Once there are no more ammunition in both guns, the loyal wingman can use the sacrifice by hitting the kamikaze with his own body frame as a lost result tool. The experiments carried out used 10 loyal wingmans and 4 kamikazes, constantly attacking. Once a kamikaze is destroyed, another one appears, maintaining a constant flow of attack. 2 experiments were performed, both for 500 iterations. In the first experiment, the behaviors on the loyal wingman's tree and its parameters were manually adjusted, so it was an experiment based on trial and error. After this initial adjustment, we used the particle swarm optimization, PSO, to tune 2 parameters, the distance engagement and distance formation. Distance engagement sets a threshold distance for a loyal wingman to leave the formation in order to pursue a threat. The distance formation is the radius of a formation, with the leader at the center. The metrics that we observed are the survival time until the game is over, the enemies destroyed by the loyal wingmans, the number of loyal wingmans that survived an iteration. And from these metrics, we defined this fitness function that was empirically defined, and we applied this function to be maximized by the PSO algorithm. First, assuming a reference to analyze the results, the fact that 10 loyal wingmen were used have only 100 ammunition for threat elimination. That is 10 for each loyal wingman in the vaporizer gun, and that this weapon has a 95% hit probability. At a perfect case, we would get 110 kills, with 100 kills by the vaporizer gun and 10 by sacrifice when out of ammo. That gives us a long-term average of 105 eliminations. The results of the experiments can be seen in this table. In the first experiment, the agents eliminated around 90% of the total threats. This result indicates us that the loyal wingman agents, using the developed behavior tree, even with parameters found empirically, were effective as an autonomous defensive system. In the second experiment, both parameters were optimized in order to obtain the highest defense effectiveness. The agents in total eliminated an average of 102 kamikazes. That's close to 90% of the total threats. This experiment also resulted in a better survival time, 27% longer, and resulting 20% less loyal wingman survivors at the end of the iteration. This indicates us that the loyal wingmen were more effective when the parameters were optimized. Now I'm going to show a short demonstration video of our simulator running. In this paper, we have proposed a novel defense scenario with completely autonomous low-wing UAVs. The UAVs cooperate to engage and neutralize a swarm of kamikaze drones. Decision-making methods were employed to allow these applications to be autonomous. Both the intelligence for a low wingman and for a kamikaze have been developed. We have seen threat elimination of around 93% after optimization. We also developed a simulator for proper evaluation of these techniques. With simple engagement rules, we have seen the emergence of teamwork for threat neutralization, with low wingman agents developing a specialized defense behavior. For example, a low wingman exhibits a specialized behavior to defend the leader. Formation and defense specifications should be further evaluated. Consensus algorithms may also be investigated. Reinforcement learning may also be applied to have more complex behaviors. Tests with realistic physics for further evaluation shall be performed, since in this project we have focused more on the development of the decision-making. I would like to thank Embraer for my scholarship, and I would like to thank you for your attention. These are the references. Thank you.
Great. Thank you, Luis, for the nice presentation. One of the questions I would make for you, you could, as a next step, it's how accurate is your simulator if you have good models when we think about aerodynamic models and dynamic models. Can you tell us something about that?
Yeah, sure. For the simulator, we didn't focus too much on the development of realistic physics and realistic models, since we are working with our own computers, and the simulation with a more complex realistic and realistic physics would demand too much of our hardware. So we are working with 15 agents at the same time. So for proper evaluation of 15 agents, we had to reduce a little bit of the realistics and focus more on the decision-making techniques for this. The next step for this project is to develop a more realistic simulator using 3D physics and something like the MATLAB UAV simulator or ROS with Gazebo. Thank you for your question.
Okay, I'm sorry we don't have time for more questions, but later on you can contact the author, and it's a very nice job, please. Thank you. And now for the next presentation, I would like to invite Pedro King. The paper title is Unmanned Aerial Vehicle Framework for Algae Monitoring. Pedro, are you here?
Yes, I am here. I did submit a video as well to.
Okay, so we are going to ask Julio to play the video, please. Thank you.
Hello, my name is Pedro King, and I will be presenting the Unmanned Aerial Vehicle Framework for Algae Monitoring. The algae overgrowth is a recurrent issue in many lakes and reservoirs. They endanger the local ecosystem. This process is known as eutrophication, and it happens for diverse issues. That could be for the introduction of macronutrients in the water and other disruptions that man can make to create an environment that is prolific for algae reproduction that goes out of control. This work proposes a framework for monitoring these algae with remote sensing using UAVs, since traditional monitoring techniques rely on field sampling, which is labor-intensive, time-consuming, and costly. And since we already have access to some experiments that proves that UAVs are reliable agents for remote sensing for vegetation specifically, we created this framework to facilitate the process of developing this algorithm. Basically, the framework has 4 major elements: the coverage algorithm, the algae detector, and the UAV action control and master node. In this presentation, we are going to cover the most relevant of them, which is the coverage algorithm, algae detector, and master node. The UAV action control isn't going to be described here since it's mostly an interface to connect with other frameworks that we are fitting in the project. Starting with the coverage algorithm, the algorithm used here was this exact cell decomposition, in which the area that is supposed to be covered is broken into smaller pieces. Here, as you can see in this image, we can see a blue square that is defining the total area that the exact cell decomposition is going to break, and the red squares, rectangles more precisely, are the areas, smaller areas we break in, and red dots represent the centroids of these rectangles. The rectangle's size is defined by the image that is covered by the camera at certain altitude, which can be calculated knowing the factors, the elements and parameters of the camera and the height in which the UAV is flying. In this case, this big square is broken into several frames in which the UAV is going to sample the algae. So the coverage algorithm, once it breaks the area that is supposed to cover, it's going to return to the master node several of locations to be visiting, which is represented by the red squares. At each of these rectangles, the UAV is going to take a sample of the image that is looking just down below of the UAV. Once reaching any of these, the locations set by the coverage algorithm, the camera that installed in the UAV is going to take a picture and is going to make the image segmentation. Typically, a real image is very hard to segment and relies on artificial intelligence, but here, since it was simulated in an environment, it was rather easy to be made with the image thresholding. So as a proof of concept for this framework, we used this technique. As a sample of the image color thresholding, we obtained this image here, these 2 images. The left is the image of the capture by the camera, and the right image is the mask of the algae. With this mask, we can calculate the centroids of each of these white areas, and the centroids are going to be delivered to the master node as well as locations. So both remote sensing and the coverage algorithm returns to the master node a locations or a series of locations to be visiting. In this case, these locations are going to be mentioned as sampling positions. And then there's the master node that is responsible for managing all services, raw services. including the actuator commands and the acquisition of data from the sensors, and activating the services of coverage algorithm and the remote sensing algorithm. Since both algorithms, the remote sensing and the coverage, gives essentially the same information, which are positions to visit, the master node uses the nearest neighbors to optimize the total length necessary of displacement to visit all the nodes. That said, the algorithm, the nearest neighbors, can be implemented in two ways. The offline strategy, in which the UAV visits all the locations and then sample the positions, and the online strategy, in which it's gonna, as it visits the sampling, the remote sensing positions, it also immediately visits the locations, the sampling locations, as it acquires it. So this is the structure, the overall structure of the algorithm. This is represented in green. The master node takes controls of the UAV control action, coverage algorithm service, and algae detector service. It's connected directly with the MRS, which is a library that describes drones elements, and it's simulated in Gazebo to test the hypothesis. Lastly, there's this test environment. The test environment was generated using an algorithm and Gazebo. It essentially created these algae samples. As we can see, these algae flocs were randomly distributed across an area, and for testing the algorithm, we used these randomly generated maps and tested the total displacement necessary to sample the algae using the offline strategy and the online strategy. This allows us to test in different conditions and not rely on specific maps to visualize the results. Unfortunately, by the design of the algae and water, it was very impractical to take a whole picture of a map sample, since due to the size of the map, it would require the drone to be flying at a very high altitude, and this would be making the algae essentially invisible to the camera. So as a display of a result and a map, in comparison between these two methods, we have these two images. First image, the top one, shows the offline technique, in which the blue rectangle, the blue lines, define the area that the UAV is supposed to cover, the total area. The red rectangles are the image, the coverage image of each sampling point given by the coverage algorithm. The green lines are the trajectories that the UAV made, connecting the dots to the positioning. And the green dots are the algae samples positions that we found using the remote sensing technique. So the first one you can see as it goes from every red dot first, then visit all the algae at once, configuring the offline technique. And the second image, we can see that at each red dot, it samples all the algae that is within the coverage area, and then proceeds to the next area to sample. Two frameworks had very similar results. The online technique taking a little bit more displacement to do the same mission, about 5% on average after 5 simulations, which is not a considerable difference. Future related work, there is ample opportunity to create more works with using this framework. We plan on using other image detection, as we know that real images will require more than color thresholds to identify and segment, as we did on this work. It's also possible to make a physical implementation of the framework, testing other coverage algorithms to find and sample the images, and adapting the framework for a multi-UAV platform. Thank you everyone for your time.
Thank you for the nice presentation, Pedro. Let me check if you have some questions. Up to now, no questions from YouTube, but I have a question. It seems it's a huge teamwork in this project. And the main goal was to take part in a competition. Was that?
Yes, it was. Initially was a part of a very big team with several segments, from aerospace engineering to computer science teams, to create a drone that is capable of detecting algae automatically using images, using the images acquired by the remote sensing.
Good. And it seems that you're planning to use different kinds of drones for different parts of the mission.
Yes, that included a multi-UAV platform, and that for that we used a different drone that was actually capable of landing in water and without damage, and actually perform the task of sampling the algae.
Yeah, and up to now, you were running only simulations, or could you do some experimental tests with the real drones?
At this point in this project, we can actually make these real simulations. We can actually have a drone that identify real algae, and have a drone that actually, a real model that actually can land on water and sample it.
Well, that's good. So we see that your work is showing a picture of the project, the whole project. So you could, in a short period of time, go further and now have real drones flying. That's great. Good. Let me just check questions. To now, no questions. And because of the time, I think I would like to thank you, Pedro. If people have more questions about this work, feel free to contact Pedro directly. Thank you. And I'm going to call the next one. The next work is analysis of a hybrid unmanned area underwater vehicle, considering the environment transition. Okay, I think it's Pedro Miranda that's going to present. Am I sure?
Yes. Can you play my video, please?
Julio?
Yeah, I will. Just a second.
Thank you.
I'm just looking for the video here because it's a bit okay. Oh, thanks.
Hello everyone, my name is Pedro Miranda Pinheiro, and I'll be presenting work analysis of a hybrid unmanned aerial underwater vehicle considering the environment transition. This work is a partnership between Universidade Federal do Rio Grande and Instituto Federal de Educação, Ciência e Tecnologia Sul Rio Grandense. This work was done by Vivian Alok, myself, Professor Paulo Drius, Professor Mauro Cunha, and Lucas Tustenhagen. I'll start now with a brief introduction. In the last years, there has been a growth in industrial robotics. This means that now robots are filling high-risk roles that used to be occupied by humans. These robots, as we can see in the figure on the right, are helping us to acquire data in these tasks. Some of these robots are unmanned aerial vehicles, UAVs. UAVs can achieve high speeds, since they face fewer obstacles when compared to ground vehicles. These usually have a light weight and are suited for inspection, surveillance, and mapping. We also have unmanned underwater vehicles. These are strong and can withstand high pressures, and they are usually neutrally buoyant. These vehicles are suited for inspection, marine biology tasks, and search and recovery. Hybrid unmanned aerial underwater vehicles, HUAVs, are a combination of the two previous vehicles. This is a new field of study. These vehicles combine characteristics of the previous ones, like waterproof and lightweight. These vehicles are suited for inspection of partially submerged structures, such as bridges and oil platforms. They can also perform search and rescue missions and monitoring tasks. Nowadays, hybrid missions are performed by UUVs and UAVs in a cooperation. However, it needs two crews and they generate separate data sets. It also needs a lot of planning, since they need support ships and crews, meaning that they take a longer time to be deployed. Having one vehicle would enable us to have one crew, one data set, and a faster deployment. In the AUV's development, we face drastic changes in fluid-specific mass, payload limitation, waterproofing, and corrosion resistance. Analysis of a hybrid unmanned aerial underwater vehicle considers UAVs can inspection pressures, and they are usually neutrally buoyant, done by Vivian Alocchi, myself, Professor Paulo Drius, Professor Mauro Cunha, and Lucas Tustenhagen. I'll start now with a brief introduction. In the last years, there has been a growth in industrial robotics. This means that now robots are filling high-risk roles that used to be occupied by humans. These robots, as we can see in the figure on the right, are helping us to acquire data in these tasks. Some of these robots are unmanned aerial vehicles, UAVs. UAVs can achieve high speeds, since they face fewer obstacles when compared to ground vehicles. These usually have a light weight and are suited for inspection, surveillance, and mapping. We also have unmanned underwater vehicles. These are strong and can withstand high pressures, and they are usually neutrally buoyant. These vehicles are suited for inspection, marine biology tasks, and search and recovery. Hybrid unmanned aerial underwater vehicles, HUAVs, are a combination of the two previous vehicles. This is a new field of study. These vehicles combine characteristics of the previous ones, like waterproof and lightweight. These vehicles are suited for inspection of partially submerged structures, such as bridges and oil platforms. They can also perform search and rescue missions and monitoring tasks. Nowadays, hybrid missions are performed by UUVs and UAVs in a cooperation. However, it needs two crews and they generate separate data sets. It also needs a lot of planning, since they need support ships and crews, meaning that they take a longer time to be deployed. Having one vehicle would enable us to have one crew, one data set, and a faster deployment. In the AUV's development, we face drastic changes in fluid-specific mass, payload limitation, waterproofing, and corrosion resistance. In this work, our proposed model can help us to have a better understanding of these two characteristics, the drastic changes and the payload limitation. I'll be presenting an AUV mathematical model and an environment transition model. I'll be also showing some simulation results. Now for our related work. To the best of our knowledge, there are no works focusing on the transition model for AUVs. However, we have in the literature two works that treat this problem. Ma et al. From 2018 treats the transition as a linear variation of buoyancy, added mass, and drag forces. And in the work by Havel et al., also from 2018, they have a continuous dynamics, density as a system state, and discrete jumps in density. Also, in our previous approach from Horn et al. In 2020, forces and moments were modeled as functions of the current environment of the vehicle. And therefore, we had a discontinuity at z equals 0, leading to an abrupt change in forces and moments during transition. I'll be showing you our AGUAUV dynamic model. This is our concept. It's called Hydrone. It has 4 vertical actuators for the air, and it has 2 vertical underwater actuators and 2 horizontal underwater actuators, meaning that Hydrone needs a passive stability underwater. It can be achieved by placing the center of buoyancy above the center of mass of the vehicle. These are our forces, moments, and our coordinate frame. Now I'll be showing you our Newton's second law equations. First, for our aerodynamic model. And these are our forces and moments for the aerial model. Now for our underwater dynamic model, these are the equations. This is our passive stability moment, where dGe is the distance between the center of mass and the center of buoyancy. And these are our forces and moments for the underwater dynamic model. Now I'll be talking about our environmental transition model. The challenge here is that the change in volume is difficult to be evaluated given the current pose of the vehicle. Therefore, we propose a solution where we consider a change in specific mass as an indirect way of consider the change in volume. This is our linear transition model, and we can observe that it saturates the environment density when the vehicle is fully on water or fully on air, and it has a linear transition. The linear transition starts and ends at a distance that is equivalent to the main hub's half height. Using this model, we intend to attenuate the rate of change in forces. We want to have a more continuous system behavior and keep the vehicle characteristics. Now I'll be showing you our experiments. These are the parameters used in the experiments. And our first experiment is a drop test, where we simply drop the vehicle from a certain height with no actuation. These are our results. And we can observe that we have the same slope for the curve of when comparing the results of the original and the new transition of the vehicle's model. We can observe that the new transition has a smoother behavior, and the acceleration is more coherent and approximates the real acceleration of a physical vehicle. When we look at the forces, we can also observe that we have a smooth but continuous behavior, and we also have smaller drag forces during the transition, which is expected. One of the problems with our model is that it is not able to achieve a null velocity. This is due to a lack of drag due to a simpler formulation. Therefore, our model is not suited for low speeds. However, it is still smoother than the previous model. Now, I'll be showing you our results for a drop test with 30 degrees in roll angle. We can observe the same behavior as before, but now we have the passive stability working on the roll angle. We can observe this smooth behavior and the passive stability actuating as soon as the vehicle touches the water. Now, for our conclusion, we propose the model that presented a smoother, more continuous behavior. And therefore, we understand that we approximated the characteristics of a real system. For our future work, we want to bring the transition model that considers the orientation of the vehicle. We also want to include higher terms and forces. And we want to control the high drone concept in the transition zone. Thank you all, and thanks to our sponsors. Thank you.
Thank you, Pedro. It's a very interesting work, and I see that you guys in Rio Grande do Sul like to work with very difficult stuff.
Yeah,
I don't think it's easy to develop a drone that can fly and can swim. It's like a duck for me. But I would like to hear from you something about the embedded sensors. It's not for now, it's future steps for sure. But I was thinking about you are flying, and then you have this transition when you are starting to swim, and you need to detect the obstacles underwater. You need to detect obstacles above the water. How are you planning to do this? Because it's always hard to have good sensors embedded in a drone. It's like, you know, the payload is low. How are you planning to do this?
Yeah, so the payload is really the key here. We are currently studying some ideas. We are really good at, we have a lot of know-how in underwater sensing. So we have already some works that are working with sonars and sometimes some kind of visual odometry. So we are still figuring out the underwater part, but really the payload is the key here. So we have to be able to manufacture a vehicle that can both be waterproof, which it's a real challenge because we have a lot of stuff, electronics in the vehicle, so we have to keep it sealed. But the underwater is a real challenge, but we understand that the next steps is really being able to make the transition. Some universities in the United States, in China, they already have done it, but they are always doing this in pools, so they have a clear water, and the sensing is a bit easier. I believe they are also working with tethered vehicles, so they have a good communication with the vehicle. That is a great challenge too. So we are still figuring out. It's really it's a big challenge, but we like big challenges here. So we will be working in this project for a good time, I believe.
Yeah, for sure. But I would like to congratulate you. It's a nice work.
Thank you. Thank you.
Thank you. More questions. I will ask people to contact you directly because of the time restrictions we have here. Thank you.
No problem.
Indeed.
Thank you.
And the final paper in this section will be engagement decision support for beyond visual range air combat. I think João Dantas is here. Okay, João.
Hello.
Would you like that people play your video, or you are present by yourself?
Yeah, you can play the video, please.
Okay, so good.
Hello everyone, I'm João Dantas. I represent the work developed with the researchers André Costa and Diego Geraldo, and with the professors Marco Máximos and Takashi Yoneyama. The work is called Engaging Decision Support for Beyond Visual Range Air Combat and was developed in the context of the project Aerospace Simulation Environment from the Institute for Advanced Studies, a research organization of the Brazilian Air Force. The air combat may occur in two primary forms, within visual range, WVR, and beyond visual range, BVR. This second one is recently more developed in the operational context due to the more extensive availability of advanced weapons and sensors. The modern air combat usually begins with BVR combat, which is frequently the most critical phase since it provides advantages and drawbacks for succeeding stages in the combat. There is no clear definition of the distance to separate these two forms of air combat, but typically BVR air combat takes place between 40 and 50 miles, nautical miles, which is related to the range of the missiles used in this type of combat. BVR conditionals force the pilots to rely more on a series of systems and subsystems to compose their situational awareness, allowing them to make tactical decisions during the combat, such as whether to fire a missile or not. Since BVR combat is rarely observed in practice, with low availability of historical data, much of the assessment of these possibilities must be done through simulation. Therefore, this work contributes by developing a decision support tool for pilots in BVR combat situations based on simulated data, with a particular focus on solving the problem of deciding when to engage a specific enemy aircraft, which is commonly based only on pilot experience. There are several previous approaches that relate to BVR combat and support decision systems, mainly provide different forms of modeling pilot behavior. The approaches found in the literature were based on Bayesian networks, fuzzy logic, agent-based modeling, influence diagrams, reinforcement learning, artificial neural networks, evolutionary algorithms, minimax method, behavior trees, and game theory. Among all of these approaches, the Haas work related to game theory from 2018 is the one that more directly focuses on estimating firing moment, which is done through a probabilistic function of the target evasive path, the missile's speed on the final approach, and the occurrence of the target's information to guide the missile. However, this methodology has not been tested in simulations with a higher degree of fidelity concerning actual BVR combat. As alternative, our work uses supervised machine learning models based on decision trees using XGBoost library to provide pilots with parameters that improve their situational awareness in air combat from data collect from simulation of operational scenarios, allowing them to better decide when to engage a specific target. Compared to most of the approach, this study was conducted through higher fidelity simulations, providing features in systems and subsystems such as models of 6 degrees of freedom, a multi-role combat aircraft model, the electronic warfare device, the data link communications, and the active radar guided missiles. This study is therefore developed around 4 main subjects. Determination of BVR air combat scenarios that will be analyzed, carrying out simulations based on the specific scenarios, collecting and analyzing the data generated in the simulations, and finally using machine learning techniques on this data to improve the pilot's situation awareness by providing information about the analyzing air combat. The agent's actions are managed by a set of rules that describe a pilot's main tactical behaviors during a BVR combat. And this set of rules is modeled as a finite state machine. And each stage is one of the possible tactics that can be taken during a BVR combat. There are 4 different states here. You have the combat air patrol, the cap, the commit, the abort, and break. The cap consists of performance a flight pattern describing an orbit around a specific position, called cap point, which we have defined heading and directions. The commit tactic consists of agents engaging a target, detected by its radar or shared by data link. In the abort tactic, the agent performs a defensive maneuver to move away from his priority threat. And finally, when the agent sensors detect a missile threat fire in its directions, it performs the break tactic, which consists of defensive maneuver describing a curve with diving with great acceleration. At the engagement moment, the agent assumes the commit behavior. Then, when the agent needs to do a defensive movement, it's assumed break or abort. Therefore, the engagement time in a simulation is defined as the time between the first commit carried by the agent and its first break or abort. We create an operational index that determines the quality of the actions taken by the agents in a BVR scenario, which was calculated during the engagement period and can be extended to any moment in the simulation. And this metric is referred to as the DCA index. Concerning the DCA index, we define this index as a probability of success ranging from 0% to 100% for BVR combat on defensive counter missions, whose objective is to establish a cap. And these missions have the goal of defending a point of interest, which is done by ensuring that the opposing aircraft are kept far away from it. In addition, it aims to do that while launching the least number of missiles possible. Besides, from the doctrine perspective, it is a good practice for defending aircraft to stay close to its cap point, since it's easier to employ tactics to defend the point of interest. From these considerations with respect to the DCA mission context, we define 3 basic principles to follow. The first one is minimize the number of missiles launched in the mission. The second one, minimize the reference distance from its cap point. And the last one, maximize the distance of each enemy to the cap point. About the equation of the DCA index, firstly, concerning the number of missiles, the ratio between the number of available missiles and the total missiles and you have in the initial of the simulation is one of the factors of the DCA index. Secondly, regarding minimizing the distance between the reference aircraft and the cap point, we consider that the decay of this effect is not linear, As the distance increases, its influence becomes much less relevant to accomplish the mission goals. Therefore, we choose sigmoid functions to generate such a decay. Lastly, when considering the opposing aircraft distance, we use a similar sigmoid function, but with opposite characteristics, since the idea was to increase the enemy's influence when they are close to the cap point. With the composition of previously calculated factors, it's possible to obtain the DCA index final calculation. In order to do the simulation sampling, use the Lightning hypercube sample algorithms. And 3,729 constructive simulations were generated in the aerospace simulation environment. In a total of 10,360 engagements were observed. Each simulation corresponds to a 12-minute scenario executed 3 times faster than real time, lasting approximately 10 days in total. The scenario consists of 2 opposing formations with 2 aircraft each, BVR 2 versus 2, which are initially approached to disengage and outside of the radar range of each other. Their main goal is to establish a cap at the same cap point, invariably leading to a confrontation between them. When they enter the limits of the opponent's radar, the engagement phase begins. In the modeling proposed in this work, each aircraft is equipped with 4 of the same type of medium-range missile, which they can achieve 40 nautical miles in range. The main variables that coordinate the simulation of BVR combat were analyzed, and 17 input variables and 1 target variables were determined to be the most important to define the simulation proposed. We'll have then the distance between the aircraft, the aspect angle between the aircraft, the heading variation, the altitude variation between the aircraft, the main aspects of the weapon engagement zone, which is estimation of the missile maximal launch range. We define thresholds before and after firing a missile, which represent a level of risk acceptance that the agent is willing to accept. The shot distance, which is the minimal distance to fire a missile. The presence or not on the aircraft of a system defined as radar warner receiver, which is an electronic warfare system that detects electronic magnetic emissions from opposing radar systems. The shot philosophy, which has orientation defined during the mission planning before the flight, referring to the moment within the shot distance launching a missile. And in the model proposed, the target variable is the DCA index of the reference aircraft in a specific engagement. About the supervised learning model used in this work, we employ the XGBoost, which is one of the most used algorithms by data scientists, presenting superior results, mainly in forecasting problems involving tabular data. In the model, 2 pre-processing steps were performed on the data, label encoding and one-hot encoding. Also, feature engineering was applied to make the training process easier to the proposing regression model. Grid search was employed as well to do the hyperparameters tuning of the model. And the root mean square error and the coefficients of determination were chosen as metrics since they are well established in classical regression analysis. We perform a dataset training validation task split, allocating 80% for training validation and 20% for the testing, and we employ a tenfold in cross-validation as well. Concerning the model results, the means of the all tenfold metrics used to evaluate the best model at the end of the grid search training process after performing the cross-validation are respectively around 5% and 80%, while their standard deviations are 0.09% and 0.77%. Considering that this is a regression problem and that we're trying to predict the DCA index, which indicate a probability of success in this type of mission, the results seem like pretty good for this type of problem since they will be making predictions with errors in range of 5% with a instantaneous inference in time, which is desirable for real-time application. So our conclusions is through simulation data, it's possible to improve the employment of the best operational tactics for each situation in the complex context of the BVR combat. Besides, it contributes by avoiding the incorrect and careless use of the weapons, improve the DCA mission effectiveness. Finally, since the pilot's survival is a determining factor, it could decrease the number of friendly aircraft lost in real-life BVR combat. Future work should move towards using a more significant number of simulations. Furthermore, the search for more variables to define the agent stage at the beginning of the engagement could improve the performance of the proposed model. Also, comparing the results of the XGBoost model with other regression algorithms would be interesting to understand which supervised learning method best suits to this type of problem. Finally, the conception of other operation metrics like the TCA index, or a combination of several of them to measure the level of performance and engagement, could contribute to bringing more information to the model. This work was supported by FINEP, and Professor Takashi Yoneyama is partially funded by the National Research Council of Brazil.
Okay, thank you, João, for this very interesting presentation. I'd like to congratulate you and the Brazilian Air Force for investing on this area. I think it's essential for our country. It's really important for us. Let me check if we have questions from the YouTube. Not at this moment. I would like to make a short question for you. How accurate is your model, the models that you're using in your simulator?
Yeah, it's a good question. Like I said in the presentation, this work is alternative because you're using high fidelity models, right? So normally the simulations about the defense and application in air combat, they're quite simple because they try to, just get a big picture of the scenario, not specific about the systems and subsystems that are embedded in the aircraft. So in Air Force right now, you're trying to give a better approach about that, giving more information, we are trying to using in a given approach and all systems that compound this kind of scenario. So you, like I said in the presentation, you have like 6 degrees of freedom in the aircraft, all the communications about radar warning receiver, the data link communication. So you try to give you a really nice approach about the systems using, and try to give you for the Air Force, for decision makers in the Air Force, a good perspective about the results of the simulation using for make decisions like each component is better to buy, for example, each aircraft is better to buy to include in the air combat scenario, the real air combat scenario, right?
Yeah, I agree with you because it's a key point. If you don't have a great model, so how can you take a decision? How can you help the big bosses to take a decision? So it's really essential. I'm sorry, I would like to spend more time here talking to you because this subject is very interesting for me, and but no, we don't have any time anymore. So thank you indeed, and now we conclude our section, and maybe Julio.
Yes, thanks, Professor Becker. I think this concludes the section. I will just play this splash screen. The next chair is already here, is Professor Alcina. So I will just for him to start the section when he is ready.
Okay.
Thanks, Professor. Professor Sina, are you there?
Julio?
Yeah, can hear you.
I have a problem with the drive. I can't read the name of the articles.
Okay, we'll try to send you a list of the names.
Okay.
Via WhatsApp, just a second.
Thank you.
So, Professor, if you can ask the presenters if they want me to play the video,
okay.
I will be here to help you if anything helps.
Can you see me? No. I have a problem with the camera here.
No, we can't see anything. It's a black picture.
Can you activate my camera, please? No.
No, I can't. I can't do it from here. I can try to stop your video and then you can try to start it again. I will try it. No, I don't think it's working.
Oh, this is working. The computer is started.
Okay.
Oh.
And maybe you will need to re-enter the meeting so the video will work okay.
Maybe. Again, let's try again. Travo geral.
People of the organization, Bruno is saying that you can start the session without video if you want, so we can carry on with the program.
Okay, so Julio, can you hear me?
Yeah, it's fine. It's fine now.
Okay, is that I'm talking to Professor Pablo Alcina on WhatsApp, and he says that he's having some difficulties with his computer. So
He joined. He joined already. Maybe he can.
Okay.
Professor
Alcina, do you hear us? We are running a little bit behind the schedule.
Yes, I am hear you.
Oh, okay, right, great.
But the video is not beginning.
Yeah. According to your okay. now we can see you are in Mars. Okay, nice.
Now explain it. You are on Mars. That's why it took so long.
A little delay.
Just a delay. Yes.
Okay, excuse me. So let's start with our session. Control and robotic system 3. And please, I will call the first work dynamic modeling and control optimization of free-floating dual-arm space robots in task space. Who will present this work is Gabriel. Gabriel is here. Okay. You're welcome. Your microphone is muted.
I was mute. Hi, afternoon, everybody. I'm Gabriel.
Gabriel, if you want to present yourself live, you can do it. But if you want me to play the video, also you just say so.
I think I'm gonna present live. That's okay.
Okay.
So I'm gonna share my screen. Is that okay? Can I share it? My screen?
No.
Yeah, you can.
Okay. Let's try it.
Okay.
So are you seeing my screen?
Yes.
Presentation? Okay. So I think I'm gonna start. Can I start?
You're welcome.
Okay, here it goes. So I'm gonna present the work, Dynamic Modeling and Control Optimization of Free-Floating Dual-Arm Space Robots in Task Space. So a little context for my work before start. Well, the development of space technology in recent years requires space robots, to be more effective. And so in that context, we have dual-arm space robots more preferred over the single-armed ones because they can do more tasks. They can do more complicated tasks and more than one task at the same time. On the other hand, we have the free-floating space robots having some advantages over the free-flying ones because the former does not require an active control system for the attitude of its base, so it saves more energy. So combining these two attributes, the free-floating and the dual-arm, we have the dual-arm free-floating space robots, which is the center of this research. A lot of applications in this kind of system today falls into the category of target capturing and detumbling. For example, the removal of debris from orbit. So the controllers proposed in those applications, target capturing and detumbling, they require a model that is trustworthy, that is reliable for its to work. We need a good model for that, for the free-floating dual-arm. And that's what I'm going to present here. So an overview of the work, we have first, the dynamic model of a generic free-floating dual-arm space robot in joint and task spaces, a joint space closed loop with parametric optimization with PSO, and implementing the model and the control in MATLAB via scripting. We also propose in the presentation an extension of the model from dual-arm to an N-arm model of a robot. That is a robot with an arbitrary number of arms. That is also free-floating. So beginning with the methodology in the model, we have a representation, a kinematic representation of the robots of two arms. Here we have the two-arm robot, and we assign to each of the links of the joints in the robotic base itself a rigid body frame. And each of these frames, these reference frames, needs to be referenced to a single inertial reference frame, because the laws of physics of motion we're going to apply to the model, they need to be referenced to an inertial reference frame to be valid. So that's what we're going to do here. Since the robots, we are assuming that it does not interact with other objects, that is, performs a free motion in space. It is an isolated system, that is, its center of mass does not receive any external forces. The sum of external forces is 0 over its center of mass. So it does not accelerate. So the center of mass is a point of inertial reference for us. So that's what we do. We reference all the rigid body frames for each link and joint and the base, the center of mass of the system of the robot. Another benefit of the work is that we use all of the tools, all of the structure of the single arm free floating space robots, where all of the designs, the controllers, the analysis are already well established in literature. So we can just recover and transfer all of the knowledge, all of this work for this model, for the dual arm space robot. So the approach that we are using here is the same used there for the free floating single arm robot. Here we have some of the equations. We use the Lagrangian formalism to model the motion of each arms separately. So we consider the joint angles or joint displacements, the joint vector of the robot as generalized coordinates for the Lagrangian method. And we apply it to the kinetic energy of the system, of the robotic system, the Lagrange equations. And we have at the end of the extensive algebra work, a set of three partial differential vectorized equations. The first two equations of this work describe the motion of each arm A and arm B. The third equation results from the Lagrangian approach, is the equation that describes the motion of the base. We also have a second constraint of the model applied to the robotic base, which is the free floating base. It does not receive any external forces, it's underactuated, it's not actuated. So its momentum is conservated. So by the momentum conservation principle, linear and angular momentum, to the robotic base, and you get a second equation, that is the one on the right. So the first equation here on the left is the joint dynamics, which has the same structure of that's consolidated in single arm scenario. And on the right, we have the dynamic from the free floating base, which also has the same structure of the free floating of the single arm scenario, where just the term here between parentheses is added to the contribution of the second arm, which now exists here. The generalized inertia matrix for the joint dynamics, the matrix H star here, is now, instead of a single matrix, is a block matrix of 4 elements. The block matrices of the principal diagonal describes the contribution, the inertia contribution of one arm to itself. So the arm A to arm A, B to B. The elements of the secondary diagonal, they describe the contribution of one arm to each other. So it's a dynamic coupling of the one arm to the other arm. And the matrix A star describes the non-inertial forces as occurs in the single arm scenario. And these matrices here, these matrices on the right side below, HM, H0M, and H0, they describe the contribution of the manipulator of the arm, the coupling between the base and the arm and the base itself. So we have a set of two of these matrices for each arm, coupling the arms with each other and the arms with the base. So all of these terms here are already well established in single arm scenario, so I'm not gonna get into that. Now the task space part of the modeling, we have the Jacobian, which maps the joint space to task space. Again, the principal diagonal of the matrix, we have the elements, the kinematic contribution of one arm to itself. In the secondary diagonal, we have the contribution of one arm to the other, the coupling kinematic scenario also. Again, the matrices below here are the ones that appear in the single arm scenario. So we build the model for the with the dual arm, using elements and the method and an approach that is already well established for the single arm scenario. We implement this model here, this equation in joint and task spaces in MATLAB, as I said before, via scripting. Here we have some of the results. The chart above, we have the comparison between the set point trajectory for each of the joints for each of the arms with a controlled trajectory, that is the output of the controller, the controlled system. And we noticed that the trajectories for reference and obtained, the controller, are overlapped. They have pretty much zero error. Since that we're working under nominal conditions without any disturbances or noise, only to validate the model, that is expected. We have an excellent trajectory tracking performance for this controller, which is the computed torque approach. And we designed the computed torque optimizing its gains, proportional and derivative gains. In the fitness, using a PSO algorithm, the particle swarm optimization algorithm, where its fitness function is precisely measures or seeks to minimize the trajectory tracking error. So that's why one of the reasons the controller works so well, like it did here in the simulation. Some other motions, graphs of motion of the model. We have the dynamics of the base. On the left, you have the rotations, the right, the translations. We notice that the base does not rotate under these set points that I put here. Since the angles, the three angles are really close to zero, we can assume that we can conclude that the base does not rotate under this stimuli. The graph below, we have the position of the center of mass, the position history of the center of mass over 5 seconds of simulation. We see that the position is pretty much constant, does not change. That is, corroborates our hypothesis that the center of mass does not accelerate, does not move actually. So we have at least a level of internal consistency in the model. We have the model according to the model itself. Center of mass does not move. So therefore, it's a valid inertial reference for us, which is according to our hypothesis and laws of physics, of course, since the system is isolated. Finally, we have the results, the position for both end effectors, arm A and arm B. The graph, the chart from above is the relative position, XY, and the graphs below are the position over time. I want to highlight here that all of the motions of the elements of the model of the robot, the links, the joints, page itself, all of them, they follow the same pattern, the same shape. They are fifth order polynomials, which is also the set points with endpoints, velocity, accelerations, both zero. So all of them have the same format, the same polynomial formats because of the set points. And after that, main contribution of the work is that we can extend this model to an n-dimensional space, an n-dimensional joint space. That is, this model, these equations right here, of course, with some modifications, they work just fine for a robot with an arbitrary number of arms. For example, this equation here, this matrix H star, generalized inertia matrix, for the n robots, we have n square block matrices. For example, robots with 5 arms, also free floating. In that case, the 5 arms example, all of the matrices in the principal diagonal describes the contribution of inertia of each arm to itself. The matrices outside the main diagonal, the principal diagonal, describes the contribution of one arm to each other and then coupling. For example, the block matrix is in the context of 5 arm manipulator. In the second line and third column describes the contribution, the coupling between the arms 2 and 3, and so forth. The matrix below, we have the C star, non-inertial forces computed from the H star matrices. Again, the terms, the formats that builds the Jacobian matrices, the recurrence relations, and the base dynamics here below with contributions of each coupling matrix from the base to the arm. So each matrix H0M here in this term below describes the contribution of each arm to the base. So here, this model here can couple an arbitrary number of arms to the robotic base, which is self-floating, which can be very, very useful for future applications where we can put more arms in the space robots, which will be necessary with all the developing space technology that is occurring today. So as actually future work, we intend to implement this model and do some analysis over it, like the singularity analysis, which is very little work in literature, very little research in the area. We intend to do it research singularities of the joint space in an N-arm robotic manipulator, which we believe will be very useful to the research field and the applications in the future. That concludes the presentation. Thanks for the attention. I open for questions if we have time now.
Thank you, Gabriel. Nice work, excellent contribution, extended the formulation to any arms. Excellent. Professor Julio, we have any questions in the chat?
Not in the chat, no.
Okay, I have one doubt, Gabriel.
Yes.
In the particular results that you present, both arms execute this symmetric task, okay?
Yes, in the model that I performed, yes, but it's not required for the model to work that both arms perform a symmetric task. They can perform different tasks. It's not a restriction to the model. But I simulated that condition. Yeah.
Okay, my doubt is you specified the task in joint space or in task space?
In task space, we enter the joint, the required trajectory for the end effectors, both end effectors, and do inverse kinematics procedure to convert the set points for joint space, we control in joint space, and reflect back to task space.
Perfect. So if the move in a asymmetric task, there is no problem if the configuration of the robot change the orientation of the base with respect to an object to be manipulated.
No problem at all. The model can follow any trajectory that I input. Of course, outside the singularity region, there are singularities that work according to the model that needs to be worked through, but the model itself can receive any trajectory task space.
Sensational. Okay, thank you. So let's go to the next work. Discrete movement control of a bio-inspired multi-legged robot that will be presented by Felipe. Felipe, are you here? Okay.
Hi everyone. Can you hear me?
Yes.
Good afternoon.
Can you? Do you want to
I will present.
share your presentation or we play your video?
I will present right now.
Okay.
Could I share my screen?
Yes.
Perfect. Just a sec, please. Can you hear my presentation?
Yes.
Perfect.
And try F11 to full screen.
Perfect.
Function 11.
Okay. Can I start?
Yes.
Very good. Hi everyone. Today we'll present the paper Discrete Movement Control of a Bio-Inspired Multi-Legged Robot. This work was developed by Elton Nogueira, me, Felipe Oliveira, and José Pio. This work was developed from the R&D project Impact Lab between Motorola Company and Federal University of Amazonas in Brazil. Bioinspiration allows the use of nature as a source of inspiration for developing new computational techniques. Besides this, it provides examples to solve numerous real-world problems efficiently and elegantly. Many relevant problems are addressed based on behaviors and mechanisms found in nature, such as ants, birds, or even the brain. For example, the way ants cooperate to solve problems quickly, the way birds fly information to optimize aerodynamics flight, the way the brain understands and learns patterns in different tasks. In mobile robotics, many problems have been the focus of extensive research efforts, such as localization, mapping, path planning, and multi-robot cooperation. However, to solve the mentioned problems, it's paramount to take into account the environment and robot properties. For example, a wheeled robot navigating in an unstructured environment. In this sense, as an alternative, bio-inspired legged robots can be applied for efficient navigation, since in nature, legged living beings can move safely and in different types of terrains. So, take into account the mentioned before, the problem we are tackling is how to model the leg movements of a hexapod through different events for 3 different gait movements: tripod, wave, and ripple. So, problems related to bio-inspired locomotion control are of significant importance and have been the subject of intensive investigation. Regarding bio-inspired robots, we highlight works with different bio-inspiration architectures like snakes, fish, dogs, insects, bipeds, and hexapods, as we can observe. Additionally, some works based on bio-inspired approaches use different types of sensors like force, tactile, and RGBD sensor. Additionally, some works based on take into account the locomotion problem, Ambrose et al. 2017 proposed a foot configuration assessment for a biped robot, evaluating the impact of 3 different feats in walk task. Thor et al. 2019 proposed a neural CPG controller for a hexapod robot, while Tan et al. 2020 proposed a kinematics model for different hexapod robots regarding the D8 parameters. Finally, as most related works based on FSM approach, we have the work proposed by Wu et al. 2020 that tackle the gait adaptation problem based on the terrain classification of outdoor environments. And finally, Kang et al. 2021, the authors proposed the learning of a FSM for gait adaptation using deep reinforcement learning. So, in this work, we propose a discrete event representation for multi-legged robot movements through finite state machines, FSM. To this end, we have defined a set of discrete events corresponding to the multi-legged movements regarding 3 different locomotion gaits and rotating operations. In the table below, we have the events centering legs, turn-off robot actuators, tripod gait, wave gait, ripple gait, spin left, and spin right. That's the movements. In this paper, we proposed a finite state machine-based approach. The proposed FSM is defined by the sextuple below, where we define respectively the set of events or alphabet, the output alphabet, a finite set of states, the initial state, the state transition function, and the output function. After the concepts presented before, we highlight the movement behavior for the tripod gait, where in tripod gait movement, the robot legs move 3 to 3 and can move at higher speeds. Here, we have the proposed FSM tripod gait movement. In wave gait, only one leg leaves the ground at any given time. All the legs on one side move forward, starting the rear leg and following the leg sequence. And here we have the proposed FSM wave gait movement. In ripple gait, on each robot side, a local wave comprising non-overlapping elevation phase is performed, and two opposite side waves are precisely 108 degrees out of the phase with each other. And here we have the proposed FSM ripple gate movement. The robot rotating movements are based on the locomotion of an insect and applies the tripod gate movement. In this movement, 3 legs are suspended in a triangular shape, and the other 3 legs support the robot, as we can observe in the figure. Here we have the proposed right rotation FSM, and here we have the proposed left rotation FSM. In the experiment, we have used a hexapod robot mounted with a node MCU, a servo driver with 18 channels, and 18 micro servo motors, resulting in a robot with 18 degrees of freedom for indoor scenarios, as we can observe in the figure. 3 experiments were performed. The first one evaluates the capability to combine efficiently different movement gates in the same representation. The second one, the robustness to perform different behavior movements. And the third one, the robot speed and stability of the hexapod robot. In first experiment, we validate the combination of different gates and movements through a discrete event modeling, as we can observe in the figure. Here we are combining all the proposed FSM presented in methodology. Additionally, as obtained result, we highlight the robotic software to control the multi-legged robots. In second experiment, we evaluate the effectiveness of the proposed approach, where we performed 10 predefined routines of tasks for every gate, and were observed precise and robust movements. Finally, in third experiment, we compared the navigation times for a given number of cycles, taking into account the 3 gates mentioned above. For this, we compared the average times for each gate for 10 complete cycles. Observing the table below, the tripod gate navigates faster than other locomotion gates. However, we observed in this experiment that although tripod gate is fastest, it's not the most stable movement gate through this experiment. On the other hand, the wave gate showed higher stability during locomotion. Thereby, it's possible to define the proper locomotion gate depending on the stability needed. Here, we can see the proposed methodology and architecture working. The tripod gate movement, ripple movement, more stable but slower in navigating, and wave gate. Spinning right, spinning left. In another context, suspending, going down, and concluding, in tripod gate, we can observe and highlight the fastest movement. To conclude, we want to highlight that the proposed approach demonstrates effectiveness to tackle the present problem. The proposed approach based on discrete representation using FSM proved to be feasible for world application regarding indoor scenarios. The FSM-based control can be successfully used simultaneously represent different gate movements. Experiments demonstrate the relationship between the gate movement and stability behavior. As future work, we intend to investigate strategies to classify different levels of terrain roughness using multi-legged robots, to investigate approaches to adjust the locomotion according to the terrain features and stability needed, and finally to evaluate the proposed approach in different kinds of hexapod architectures. So we would like to thank you for your attention. Thank you to Motorola support to this project, and I hope to answer your questions. Thanks.
Thank you, Felipe. Nice work, nice experimental results. So we have time for one question. Julio?
No question from the chat.
Okay, I have a doubt only. The experimental results show that the robot walks over even terrain, okay?
Okay.
But it is important. One advantage of legged robot is that they work well in an uneven terrain. On the contrary of wheeled robot, okay? So did you execute some experiments in an uneven terrain?
For this work, we are starting this new research line, considering multi-legged robots here in UFAN. So this is the first work we have performed, exploring these multi-legged robots. So we intend to start the locomotion problem and modeling. After we intend as future work to represent the environment we are walking, and we intend to represent the vibration regarding the locomotion of the robot, and using IMU or and any other sensor to represent the distance around the environment. So we intend to extend this work to outdoor environments with unstructured and unknown environments, uneven environments, as you said. So that's the first work.
And do you think that this finite automaton controller is enough to these other tasks?
I'm sorry.
And do you think that your finite automaton controller will be work well in uneven terrain?
I got it. I think that representations, discrete representations, could result in good movements and robust movements, because we know very well the movements that hexapod could represent. So if we understand that we know these discrete events and we can represent these events, so we can reproduce in a robust way how these kind of robots can move around this environment. So I saw during the development of this work some approach using learning techniques to learn FSMs, finite state machines, to represent this kind of movements. And for example, the problem is that this kind of approach need to learn how a hexapod or a multi-legged robot could move around the environment, and this results in strange movements, you know. So if you know the way multi-legged robots, especially hexapod robots, can move, So I think that finite state machines could represent very well.
Okay, thank you. Congratulations.
Thanks,
So
thanks.
we are at the end of this session, and I invite you to assist the next section, assistive robotics and human-robot interaction too. Okay, thank you.
Thank you all.
Thank you, Professor Alcina. I think we are starting soon the next session. The chair is not here. It should be. I'll check on the chair and then I will come back.
Okay, everyone. So we are waiting for Professor Romero to come up, but as she didn't join us yet, I will chair the session. Okay. Is that okay for everyone? I believe Karan Takiadini is the next presenter.
Yes.
He's going to present the work entitled, okay, let me introduce the session. This is the Assistive Robotics and Human-Robot Interaction, session number 2, which, as I said, was going to be chaired by Professor Rosalie Romero. When she comes back, she will chair the session, but in the meanwhile, I will take her place. Okay, so Karan Takiadini is going to present extended reality for teleoperated mobile robots. Okay, Karan?
Yes, hello everybody. I recorded a video. Can I share the video?
Oh, okay, Karan, we will play your video that you sent to us, okay?
Okay, perfect.
Thank you.
Thank you. Hello everybody. Welcome to the presentation of the paper Extended Reality for Teleoperated Mobile Robots, with authors Edivaldo Santos, Arturo Batistuto, Karan Takiadini, Pedro Lazari, Kellen Vivaldini, and Lydia Rocha. The agenda for this presentation is basically introduction, methodology, results, and finally, conclusion and future work. Brief introduction starts with problem definition. In smart factories of the future, robot teleoperation can be challenging and therefore impose high requirements on user training and expertise. Secondly, how to achieve higher teleoperations efficiency and safety for use cases like the remote control of robots inside factories and control of heavy machinery in risk environments such as mining. So this paper addresses human-robot interaction scenarios in which extended reality technology is used to improve mobile robot teleoperations by increasing user friendliness and minimize requirements on user training and operators' previous expertise. So let's describe the methodology, starting with the technical assets adopted in this study. First, Magic Leap 1, a mixed reality headset that contains features suitable for the experiment, like it's a standalone device that does not require a connection to PC. Secondly, Oculus Rift S, a virtual reality headset with good graphic quality, very good for this experiment. Thirdly, Ultraleap Leap Motion, a computer hardware sensor device that supports hand motions as input, designed to provide hand tracking in virtual reality while the device is mounted on VR headsets such as the Oculus Rift S. Then we have the robot ThirtBot 2i, a research mobile robot with a modular chassis equipped with cameras and sensors and host-compatible netbook. Sensors and cameras, the main component of the ThirtBot 2i for this experiment is the depth sensing camera, the model Kinect, to assist the remote control task. Then we will have HOS, the robot operation system, a flexible framework for robot software coding. And finally, Unity 3D, a cross-platform gaming tool developed by Unity Technologies that has been extended to support desktop, mobile, and XR platforms. About the architecture, the proposed end-to-end human-robot interaction network architecture includes the robot component at one side, And from human side, it includes the mixed reality and virtual reality headsets component. Regarding the functional architecture, the integration of HOS and Unit 3D is enabled via HOS bridge through a WebSocket connection. It can therefore subscribe to messages in one HOS part and publish them in the other HOS part. Okay, regarding the experiment procedure, to evaluate the robot teleoperation efficiency, we defined an experimental procedure as follows. The ability of two XR users to execute certain tasks remotely based on extended reality technologies such as mixed reality and virtual reality, compared to one user based on a traditional physical controller, namely here baseline. So we measured remote robot control using this traditional physical controller, namely baseline here, compared with virtual reality robot control based on joysticks mode using Quest 2 headset and mixed reality based on right and left hand gestures mode using Magic Leap headset. The robot view was available to testers exclusively via the video transmitted by the robot camera to available displays, the notebook for the baseline, and the headsets for the mixed reality and virtual reality modes. A very important note, measurements were limited to 3 participants due to interaction restrictions derived from COVID pandemic. Okay, about the task. The task consisted of teleoperating a robot from a control room so that it passes through a door, turns left 5 meters ahead, goes through a slightly curved path 1 meter width and 15 meters long until the parking slot. It is the end destination. And finally, regarding the measurements, we established 4 measurements to characterize the quality of service and quality of experience. The first one, operational errors. The number of times the robot hits obstacles. A note, one of the major open problems in human-robot interaction relates to human safety during collaborative work with robots, for example, in manufacturing environments. Okay, the second measurement was the completion time. That means the total time to complete the path taken by the robot. The third measurement was effectiveness, measured by how effective an XR user controls the robot along a predefined path. It is based on average completion time and number of crashes. And finally, perceptions of task difficulty to capture subjective participant response while operating the robot. Okay, let's go to the results, but before, one initial clarification. The 3 testers involved in these measurements had different levels of previous XR experience and familiarity. Thus, the average result of each control mode represents a good balance between users with low and high experience. So, the highlights of the results. Firstly, virtual joysticks gave users the advantage of clear notion of users' movement effects on the remote robot. In short, virtual reality control mode has had faster completion times and smaller number of crashes. Secondly, handling 4 keys in the physical computer keyboard control mode, right, left, move forward, and stop, has led to user confusion, especially in stressing situations. Consequently, it has fueled the highest number of operational errors and crashes. In real scenarios, this implies serious safety issues and efficiency downgrades. And finally, human-robot interaction efficiency during the path motion was best with mixed reality and virtual reality applications, as shown in the graphics, thanks to the integrated visualization of robot camera view and virtual control commands at the same advanced user view in the headsets. Last part of this presentation is conclusion and future work. In summary, this work concludes initially that the combination of robotics and XR technologies provides significant advantages over traditional robot controlling technologies. It respect to teleoperations user-friendliness, efficiency, and effectiveness. And as a consequence, human safety on the collaborative work with robots. Regarding future work, we have some proposals. First, enhance current experimental procedures with engagement of higher number of participants. So to observe if additional conclusions surface, especially those of subjective nature like user-friendliness perception. Secondly, build a functional dump in simulated type of environment, so to allow wide availability for others to repeat and add additional value to this experiment. And finally, profit from the evolution of mobile broadband technologies, more specifically the worldwide rollout of 5G networks, to enhance scope to compare the effects of wireless system communication like Wi-Fi, 4G, and 5G on the remote controlled robots. That's it. Thanks for your attention. Bye.
Thank you very much, Karan, for your presentation. Very nice work on teleoperated robotics using technologies from mixed realities, augmented realities. Very nice work. Do you have questions from YouTube? Okay, and does anyone have questions here from Zoom? Okay, so now I have a question. Karan, you mentioned several times in your presentation that one of the advantages of using teleoperated robots is safety, right? Human safety, mainly. I want to ask you, in which applications do you intend to use these teleoperated robots?
Yeah, good question. Yes, one of the use cases that we are in mind is teleoperation of robots in mining, especially in risk scenarios. As you've seen in the TV, we have several cases of people have damage in this kind of environment, right? So if you have robots teleoperated in these environments, then you can have the human being in a more safe situation. Of course, for do teleoperation of robots in this scenario, you really need a good, let's say, system communication, and a very precise devices to really control these robots. Otherwise, you can damage the robot if you don't have, let's say, a very low latency to drive the robot in mining. Okay.
So we have a question from Elio Azevedo. A crash in an industrial environment can be tragic. In a factory environment, operators are highly trained. Do you consider using these operators when increasing the number of experiments?
Yes, we have several plans for expanding our experiment. One of them is this one. So we want to really test this in a real environment and expand the number of testers, and also include another type of system communications or communication systems As I said, so we want to use 5G as we have now available. We start to have available here in Brazil for experimental procedures. So yes, hopefully I have answered the question.
Okay, Karan. Any more questions? So, okay. So thank you very much, Karan, for your presentation.
Thank you.
So proceeding to the next work. The next work is RoboCup at Home, evaluation of voice recognition systems for domestic service robots in introducing Latino datasets. It's going to be presented by Eric Brinkhaus.
Yep,
Hello,
I'm
Eric.
here. Hello, how are you?
How are you?
Fine, thank you.
So Eric,
I will.
are you going to present or you, do the presentation yourself, or do you want us to play your video?
I prefer presenting it live.
Okay.
I will
Go
try
on.
to share my screen. Okay. Are you able to see the full screen?
Yes, Eric. Yes.
Okay, good. Then, wait, sorry. I will start. So my name is Eric Greenhouse, and I will be presenting the work RoboCup at Home, evaluation of voice recognition systems for domestic service robots, and introducing the Latino dataset. This work was done by me, Federico Andrade, Guillermo Trinidad, and Matías Echeverri. We are all of the Facultad of Ingeniería from Montevideo, Uruguay. In this presentation, first I will do a short introduction of this work, highlighting important concepts of the RoboCup at Home competition, which were the motivation for this work. Next, I will go through the main objectives of this work. And later, I will talk a little bit about the systems that we select for the evaluations. Once the systems are discussed, I will introduce the datasets used for the evaluations of the systems, including the Latino dataset. I'm going to point out the most relevant results obtained in the evaluation. And finally, I will present the conclusion and future work of this project. So domestic robots are having more and more impact in the world, and in this sense, the RoboCup at Home competition tries to motivate the research in this area. In most of the challenges of this competition, the robot must interact with humans, and normally this interaction starts with a human voice communication. Therefore, it's very important that the robot understands human speaking commands. Automatic speech recognition systems are used in order to transcribe the voice commands into text and to later process it. This step is very important because if the transcript is not good, the robot will not understand the command. There are two very important factors to take into account. The RoboCup competition takes place in a very noisy environment, and the speakers have different accents. Therefore, it is very important to train the robot, consider the different accents, and to work properly with noise in the background. While we were looking at the related work, we found out that there are very few works that compare the different automatic speech recognition tools. And in particular, we did not find any work that compares the most popular tools used in the RoboCup competition. Also, not using dataset related to the competition. This is why one of the main objectives of this work was to compare the most popular automatic speech recognition tools using voice commands similar to the RoboCup challenges. Also, this evaluation could be useful as a baseline for the new teams or for teams that don't want to invest much time in the speech recognition area. When we were looking for datasets to evaluate the systems, we didn't find any dataset of non-native English voice recordings, for the exception of an Asian dataset that we also use in this work. So we decided to build our own dataset of English spoken commands by Latin people. We called Latin dataset. The first step of our work was to decide which systems we will choose for the evaluation. For this, we read the team's descriptors paper of the RoboCup competition and all the related work that we found. We decided to evaluate the pocket things Caldi, Pico Voice Leopard, and the Google Automatic Speech Recognition Systems based on the popularity. And we also want to compare only offline tools because the internet access and bandwidth are not guaranteed in the competition. Besides being an online tool, we include Google because of its popularity and also because Dublin and Rich to have an online system to compare in this work. Now I'll mention a few characteristics of the system used. Starting with Caldi, it is a toolkit for speech recognition that supports recurrent neural networks. It supports parallel training on multiple GPUs. And one very important aspect is that this tool includes pre-trained models. One of them is the net 3-chain model that was used in this evaluation. Now, Pocket Sphinx is based on Sphinx tool and was developed by the Carnegie Mellon University. It is based on hidden Markov model. And by looking at the team's descriptor papers, this is the most offline tool used among the RoboCup teams. Leopard is a tool from Pico Voice. The main objective of the creators for this tool was to create an speech recognition system being compact and computationally efficient. A free trial license was used in this work in a Linux operating system, but in order to use it in other operating systems, a commercial license is needed. For last, the Google Automatic Speech Recognition Service is the most used in the RoboCup competition, and it uses advanced deep neural networks algorithms to perform the speech to text. In our work, we include this table, which could be useful at the moment of deciding what system to use in the robot. By just looking at the table, the reader will know at least for us, the tool that was more complex to install was Caldi, and the easiest one was Pocket Sphinx, which got installed using a simple command. It will know also that except for Leopard, all tools have a ROS package to make the integration with the robot easier. Also, Caldi and Pocket Sphinx are completely free, while Google and Leopard have free and paid versions. In this work, we use the tools as out of the box, but it could be useful to know if they allow some customization. Caldi and Pocket Sphinx are fully customizable regarding the models, while the free version of Google only allows what they call adaptation models, and Pico Voice only supports customization in the paid version. Jumping now in the dataset used for the evaluation, we want to use a dataset that represents the environment of the RoboCup competition. In this sense, we decided to use 4 datasets. The Fluent Speech Corpus is a native English spoken commands dataset. These commands are a combination of a place and action of an object. Then we use the Voices dataset, which is also a native English spoken corpus, but in this case, the recordings have background noise. For example, our TV or a radio turned on in the background. Also, the speakers are placed in different distance from the microphone, so it represents better the environment of the RoboCup. The counterpart for this dataset is that the recordings are not of commands, but for people reading just text. While we were investigating the related work, we found this English command spoken by Asian people. In this work, they don't put a name to the dataset, but in our work, we refer it as the Asian dataset. This dataset is composed by a list of 100 of commands repeated by 4 Asian speakers. And as we didn't find any other non-native spoken dataset, we decided to create the Latin dataset using the same command list that, of the Asian dataset. In total, we record 11 speakers. So in total, there are 1,100 recordings in the dataset. The speakers are from different nationalities. 6 of them are from Uruguay, 2 are from Mexico, and the other 3 are from Venezuela, Argentina, and Chile. The idea is to keep maintaining this dataset, including more people and also more people from other countries. All the datasets have similar structure. The commands have similar structure. For example, go to lobby, move to dining table, finally leave the apartment. In most of the cases, there is an action, a place, and an object, but it could vary, as this example that has 3 actions and just places. Before jumping into the results, it is important to mention that we install all the tools in the out-of-the-box version with the pre-installed models. We didn't do any training of the models, and we execute the evaluation in a computer running Linux. And for all the tools, we use the available Python library. We use the metric word error rate to evaluate the systems. We calculate this metric for each command or text transcription, and it calculates as follows. It is the addition of the deletions, insertions, and substitutions of words needed to match the correct transcriptions divided by the total words of the correct transcription. Looking at the first graphic, we can see that Google was the tool with the best performance. Even in the fluid speech corpus, we are not able to see the media value because it's near 0. So it means that in most of the cases, it got the exact transcription. Among the offline tools, Caldi was the best, has the best media value in almost all datasets, and also the variance is lower than, for example, Pico Voice. One very important point is that Pico Voice was the best tool when evaluated using the voices dataset. This one is the dataset with the background noise. It performed even better than Google. This indicates that Pico Voice behaves better in noisy environments, but it is also very strange that it performed better in the native English with background noise than the native English without background noise. Now, looking more specifically in the Latin datasets, the results are overall the same as in the dataset where Google was the best and not so far behind Caldi. But one thing that draws attention is that Pico Voice is very inconsistent depending on the speaker. For example, for speaker K, it has the worst results of all the 4 systems. So in conclusion, in this work, we evaluate the most relevant automatic speech recognition tools, in particular 3 offline and 1 online. The evaluation was done using datasets trying to mimic the RoboCup environment. And also the Latin dataset was introduced, and it was very helpful when evaluating the systems. From the results, we conclude that Google was the best tool. Among the offline tools, Caldi was the best and most consistent, while Pico Voice Leopard showed great results when evaluating it in the noisy dataset, but was very inconsistent when using the Latino dataset. For future work, we want to keep maintaining the Latino dataset. Also, it will be very useful to create 2 new datasets with African and Oceania speakers. In this work, we use the tool as out of the box, but it could be interesting to evaluate them by adjusting parameters and by building and training specific models targeting the RoboCup competition challenges. That was the presentation of the work. Thank you everyone for listening and for your time.
Thank you very much, Eric, for your presentation. Great work, really, really great work. Many contributions for the RoboCup community. I believe your data set that you are going to make available, or that is already available, is going to be of a great use by the community. They're going to train their recognizers based on your data set. Great work, Eric.
I hope so. Thank you.
So Elio Azevedo is asking you about the Portuguese language. Is Portuguese included in the languages used for the Latino dataset or no?
Sorry, I didn't follow the question.
Oh, sorry. Among the countries from which you collected the speakers, is Brazil included? Is Portuguese included or no?
Right now, no, but if someone volunteers to be recorded, it will be awesome to have Brazilian speakers in the dataset.
Yes, it will have would be great. Nice, would be great too to have a Brazilian voices, Brazilian data set recorded in those data sets.
Yeah, it will be very interesting because also Brazil has a slightly different accent than the rest of America.
Yes, definitely. Any more questions from the audience? Questions from the YouTube? No questions. Eric, I have one more question.
I have one too.
Go ahead, Julio, please.
Okay. If I understood right, you are proposing a data set that comprehends many different pronunciation in English. So
correct.
So it means that Portuguese speakers, okay, they will have a different accent, but the language is English anyway. So,
correct. Yeah.
Okay. Oh, that's maybe one of the points that can comprehend Elio's question. So because here in Brazil you have even different accents for English speakers across the country. So
okay.
if you are I'm sure that it should be the same on most continental countries. Maybe also in Argentina should be the same. Maybe Chile could be the same. Because when it goes to south, it just sounds different. But I don't know if you are or if even the RoboCup is going this direction, but it will be very interesting to try to merge data sets of different speakers from different countries as well, like Europe, because I know by some friends that if you are like not German, but even English speakers from England, they have different accents. From German, it's not that different from English accent, at least in my hearing. But people from Russia, people from Kazakhstan, people from, and then you have already mentioned Africa and other countries. It's a very nice initiative, I think, and you should definitely aim in direction of these of different countries, and even try to make different regions inside countries like Brazil. Just a suggestion.
Okay. Thank you for
the work.
Okay, thank you for your comments.
Oh, Erica, I have one more question to close the session. Oh, I should also mention that this work that is being presented now was among the top selected works for the Journal of Intelligent and Robotic Systems. Congratulations on this too, Eric.
Okay, thank you.
Oh, great. Professor Todd has a question. Go ahead.
Yes, I have a question related to your participation in the conference. How did you hear from LARS? Because we did an effort to invite people from Uruguay and from other countries, and we are happy that you are here. And how did you hear that?
Sorry, but you asked the wrong person because I got here because of Federico Andrade, who is another author of this paper. I think he will be speaking, he will be presenting a paper tomorrow too. So I know if you are going to be present tomorrow, you can ask him this question, because he was the one who got me into this.
Yes, because I sent some emails to, I don't know, some universities in Uruguay and some robotics associations, and I am curious to know if that worked or no. And I think your project is very interesting. If you want, you can send to the organization of the LARS an invitation for people from Brazil to participate. I think it's
awesome.
Very okay. Thank you.
Okay, that will be great. Thank you, Eduardo.
Oh, okay. So just a final and quick question, Eric. I promise.
Sure.
Do you experiment with non-pre-made phrases like, or do you plan to experiment with non-pre-made phrases like do this or go to that place or find that object? Do you plan to experiment on this? Do you find this is important? I think it is important, maybe not for RoboCup applications, but more for general applications. I think it would be a great contribution too.
Yeah, I agree with you. Right now, the dataset is focused on the RoboCup, but for sure it can be muted in the future to include more phrases. Also, not exactly commands, maybe just phrases to the robot for understand. But I agree with you. Right now, we are focusing on the RoboCup competition, but yes, it will be great to keep improving it and to make the dataset bigger.
Okay, great. Great, Eric. Thank you very much for your presentation.
Thank for you for the time.
Okay, everyone. So we are closing section assistive robotics and human robot interaction 2. This is the final session for today. And we resume LARS tomorrow, starting at 9 a.m. We resume LARS with the CTDR, I believe, Julio, is going to be the CTDR on the thesis, the PhD thesis.
Yeah, starting
right?
with the remaining master thesis and then PhD thesis.
Okay, so you still have master thesis to be presented?
Yeah, yes.
Okay, so it's going to be master thesis and PhD thesis tomorrow. And then we're going to have the great talk by Professor Flávio Tonindadel. And this is going to be during the morning. And during the afternoon, we're going to have the three final technical sessions of the event. Okay. So I hope to see you all tomorrow here. See you soon. Bye-bye.
Thank you, Bruno.
Bye. Thank you.
Bye, everyone. Thanks.
Bye, everyone also. Bye.
Bye, everyone. Thank you.